Okay guys, in this video I'm going to teach you how to find all the rational roots of a polynomial function. In other words, all the points where the function intersects the x-axis, all the zeros of this function. This is a fairly long process, but it gets easier the more you do it. It's very procedural. You always take the same steps every time. There are basically 5 steps to this process. So I'm going to walk you through each of the 5 steps in this video, right? And if you do your reading and you watch this video, you should be able to do this on your own. It's not particularly hard. It's just tricky the first time. So let's take a look at a function, f of x equals x to the 5th minus 6x to the 4th plus 10x to the 3rd, no x squared term, minus 11x plus 6. So you can see here this is a 5th degree polynomial. Its y-intercept is 6. It has up to 5 possible zeros. So we're going to find all 5 if there are indeed 5. There might be 3, there might be 1. Okay, so in order to do this, the first step we will always want to take is to check for any common factors across this polynomial. You can see here that there are no common factors. There is nothing that is able to be divided from each term. So no common factors. Okay, so we don't have to worry about that. If you had like a 2 that was in each term, you'd want to factor that out. It makes your work a lot easier. As we've seen before, right, that vertical stretch factor, that common factor, does not affect the zeros of a function anyway, so we can get rid of it. Okay, really what we're doing here is setting this equal to 0 and then factoring to solve, right? So you don't have to write it down this way, but you are setting that f of x equal to 0, setting the output equal to 0. Okay, the next thing we're going to do is called Descartes' rule of signs. This is our old friend Rene Descartes, who of course came up with the Cartesian coordinate system, right? So Descartes' rule of signs. And Descartes' rule of signs is simply a way to figure out how many positive and how many negative possible zeros you have for this function. It does not tell you the value of the zeros, it just tells you how many zeros there are. So in order to do this, right, what we need to do is look at the way that the signs change from term to term as we move through this polynomial function. In other words, where does it go from positive term to negative term? So first, right, we want to count the sign changes of f of x. And that'll tell us the number of positive zeros we have. So let's look at f of x here. And we see we have f of x equals x to the 5th, which is a positive term, minus x to the 4th, 6x to the 4th, which is a negative term, plus 10x cubed, which is a positive term, minus 11x plus 6. So when we count, this is positive, right? Then we go and we have a negative here, so that's one sign change, going from positive to negative. From the 6x to the 4th, the next term is also a sign change, going from negative to positive. So that's sign change number 2. Going from positive 10x to the 3rd to negative 11x, right, is sign change 3. And going from negative 11x to positive 6 is sign change number 4. So that tells us that we have 4 positive roots, 4 zeros. Okay? So 4 positive roots or zeros, right, which means we probably have 1, right, negative. Well, then we can check that, right, by using f of negative x, which we realize is going to be negative x to the 5th is going to be negative x to the 5th. Doesn't change when we put it into the 4th, right? Negative x to the 4th is still x to the 4th, so it's negative x, 6x to the 4th. It is going to change. We do negative x to the 3rd, it's going to be a negative, right? So we get minus 10x to the 3rd, right? And then we take negative x and put it in for x here. Negative 11 times negative x is positive 11x plus 6, doesn't change. So counting the sign changes, we see that we have none here in the beginning, right? None here, none here. We don't have them until we go from negative 10x to the 3rd, right, to 11x. So we have 1, which is exactly what we predicted, right? 1 negative root. Okay? So again, that tells us that we have up to 4 positive roots. So looking for 4 positive roots and one negative root. Okay, so that's step 2, Descartes' rule of signs. Again, that doesn't tell you what the roots are, it just tells you where they are, whether they're positive or negative. Okay? For the next step, we're going to use what's called the rational roots test to generate a list of possible actual roots. Okay, these are not, it's not going to tell us what the roots are, it's going to tell us what they might possibly be. Okay, so this is step 3, rational roots test. And this is pretty easy. It can be difficult depending on the particular equation you're working with, but really this is pretty easy. What you're going to do here is generate a list, right, of the factors of the first term, right, which is the leading coefficient, right? We're going to call that Q. Okay, we're going to make a list of the factors of Q. So in this case, Q is 1. Okay, and we're going to take that and find all the factors of 1. And of course, that's just plus or minus 1. We're also going to make a list of all the factors of the constant term, which we're going to call P. So in this case, that's 6. So we want to know the factors of 6. Luckily, this is pretty easy, right? It's just plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. If you had a bigger number like 72 here, right, your list would be very, very long. If you had a number with a lot of factors in it, or 144 is a nightmare scenario, or 120. Okay, but here we only have 4 possible factors. Now we're going to make a list of fractions, right, using these, right, P over Q. And this is very easy because Q is 1, right, so we just end up with plus or minus 1 over 1, right? We get plus or minus 2 over 1, which is plus or minus 2, plus or minus 3, and plus or minus 6. So because Q is 1, this is a very short and easy list. We don't have to worry about a lot of different fractions. If Q was a different number, if Q was, for example, 2, and we had different factors, we need 1/2, right, 3/2, and so forth. Okay, we'd have to do it over both denominators. We'd have a list of 8 rather than just 4. Okay? So again, just to reiterate, these are the possible rational roots of f of x. That does not mean all of them are. You can see we have 8 choices here, but we know for a fact that there's only going to be up to 5 roots. So we know we're going to not use some of these. So the next step is to test these roots and see which one of these roots will actually work in our function. Okay, I'm going to go ahead and switch to another video here. So if you just continue to watch the second video, that'd be great.